Good morning to everybody. Welcome to the mass transfer course. Today will be the lecture 8 and this is the last lecture of your molecular diffusion. So in molecular diffusion we have seen there are three types. One is diffusion of A through non-diffusing B, and we got the expression in terms of pressure. Flux, we calculate flux Na equal to dAB into P RT L PA0 minus PL by PBM, where PBM equal to PBL minus PB0 ln PBL by PB0 log mean partial pressure of P. And for equimolar counter diffusion, expression is here. Flux Na kilomole per meter square second equal to dAB into PA0 minus PAL by RT into L. And there is another thing, that is non-equimolar counter diffusion. So we studied this thing, and in last lecture we solved two problems relating to this. Now we can calculate for a particular process what is Na. Na means total flux, that is kilomole per meter square per second. Why it is a calculation of Na is important? Because if Na is high, then I get the better separation in a smaller equipment. So that's why we are interested to calculate the Na. Now if you see, for a particular process the Na is low. If Na is low, that means the separation, good separation is not possible. So if you need good separation, you need a bigger equipment. If you need a bigger one, that may not be economically feasible. Then what will be your objective? So then we like to increase this Na. Now if you see, if you want to increase this one, how we can increase this one? If I increase the driving force, okay, that will increase PA0 minus PA. Pressure, this if it is, but it is also one limitation. It will, okay, if you have a partial pressure, let's take for atmospheric unit, it cannot be greater than 1 atmosphere if all are, or if you keep some high pressure, then it will be some other way. But then you can increase at a certain level, because there will be some constraint, because if you increase the pressure, then your equipment cost also will be higher. You need the thickness of the equipment in higher side, so cost will be higher. So there is a constraint. You cannot increase this thing, driving force, in some after a certain value, not maybe one-fold, 10 times like this, not like that. Similarly, the pressure and temperature also you cannot go beyond certain limit. And this is already that we have seen, that is the boundary layer thickness. It is more or less fixed for a particular system for laminar flow. Now another thing, you can increase this flux by increasing the diffusivity coefficient or diffusivity. Because diffusivity you can change in folds, and if you can increase the diffusivity in higher level, then automatically the flux will increase. Then that means you can get the better separation in a molar equipment. So today we will talk with the diffusivity coefficient or diffusivity. Sometimes it is called DAB. So DA stand for A is diffusing through B. Okay. Now diffusivity, generally it is seen that it increases with temperature with the magnitude 3/2, 1.5, and it will decrease. It is decreased if you increase the pressure. Please understand, if you increase the pressure, molecule will be more compact, then molecule will not diffuse much. Diffusivity will be low, because putting the other molecule aside, going one molecule, it will be difficult because pressure is because molecules are very close. So if you increase the pressure, diffusivity will decrease. Now if you increase the temperature, then velocity of the molecule will increase, and therefore the diffusivity will. And this is the generic relation for gas phase diffusivity. And the diffusivity value are very important. In gas, the diffusivity, that value is order of magnitude in meter square in 10 to the power minus 5. For liquid, it is 10 to the power minus 9 per meter square per second. Gas and solid, that will be 10 to the power minus 10 to 10 to the power minus 5. In average 10 to the power minus 12 meter square. And solid, it will be 10 to the power minus 19 to 10 to the power minus 34 meter square. So you should understand that separation in gas is much easier than the solid. So if possible, always we will try to bring the component in gas phase, both the component in gas phase, then separation diffusivity will be very high. Here let's take 10 to the power minus 25, and this is 10 to the power minus 5. So you understand, 5-fold. The diffusivity will be 5-fold. That is very high. Okay. And liquid also, if you have a liquid diffusivity is as half of this thing, 10 to the power minus 5 to 10 to the power minus 9. Okay. So here it is almost 10 to the power 4 times. Whatever is the diffusivity here 10 to the power 4 times less. Here it is 10 to the power 5 times less. Here it is 10 to the power minus 20, 10 to the power 20 times less. Or in other words, it is that much of higher. So in gas, always diffusivity is high, and in general the magnitude is in where unit meter square per second. So from this picture, we should have a approach for the separation. I will get the higher flux if my diffusivity is high, and if I get the higher flux, then my separation will be easy. So I will have a tendency to bring the component in gas. If gas is problem, then gas liquid or liquid, then the separation will be easy. And generally that's why distillation process goes. Distillation means liquid mixture, I want to bring it into the gas liquid, means I am bringing this component in gaseous state so that the separation will be better. Now if you see the gas diffusivity coefficient of gas or different air methane at 273 Kelvin, that is 1.96. Similarly, some other components where A is the which component is diffusing, and the B is the solvent. So the oxygen, carbon dioxide, that is 1.85. Now if you see the highest one, that is 11.32, hydrogen in helium. Helium is very inert and hydrogen is very small variable. Then the diffusivity of hydrogen in helium will be very high, because helium will not give much endurance to hydrogen. Similarly, hydrogen in nitrogen also is high, but nitrogen molecule is much bigger than the helium. That's why it is less. But still it is high. But if you see which molecule will form some ionic bond like this, or hydrogen bond, air benzene low, then air n butanol, this is low. But if you see DAB into 10 to the power minus 10 to the power 5 meter square, that is equal to 1.96. That means DAB equal to 1.96 into 10 to the power minus 5 meter per second. So diffusivity of gases are in the range of 10 to the power minus 5 in meter square per second. Now if you see the diffusivity coefficient of liquid, the solute is carbon dioxide and water, it is 1.9 into 10 to the power minus 9. So oxygen in water, this, water in acetone, this. So this is the thing people, and this diffusivity compound, and people have done the experiment and they have seen these are the diffusivity coefficient of different systems. There is a in Perry's handbook in chemical engineering, you will get from the library, or you will get some online documents where you can see, you will get the data what are the diffusivity at 25 degrees. Okay, so diffusivity of liquid is allowed in 10 to the power minus 9 range. It is in meter square per second. Now diffusivity of gas solid, gas helium in Pyrex, that is into 4.9, okay, into 10 to the power minus 11 semi square per second. This is into 4, so 10 to the power minus 15. Okay. So this is the thing where your gas solid, the diffusivity thing, and it is range around 10 to the power minus 12 or 9 to 12 or 10 to the power minus 12. The diffusivity unit is meter square per second. Now diffusivity coefficient solid, it will be carbon FCC iron, okay, iron FCC iron. So these are the thing, and generally diffusivity coefficients of solids are in the range of 10 to the power minus 19 minus 10 to the power minus 34. Okay, so this will be the 34. So, but that's why I am giving all this thing, because you know that this is the gas system, and some way you have determined this diffusivity through some experiment, or you have calculated from some equation, or you have collected from some literature. Then you should have a feeling that diffusivity of gas means it will be around 10 to the power 5 range, 10 to the power minus 5. Liquid means 10 to the power minus 9 range. Gas solid, it will be around 10 to the power minus 12 range, and solid it will be 10 to the power minus 19 to 34. That initial judgment you should have a knowledge of how much it will be. Okay. So that's why it has been seen. So this is the diffusivity coefficient of various system varies in this range. Now second thing will be how will I calculate the diffusivity coefficient, because accurate calculation of diffusivity coefficient is very important. It is very much similar to your in chemical reaction engineering, the specific rate constant. Specific rate constant, that accurate calculation of specific reaction is very important. If there is a error, then whole calculation will be erroneous. So that's why in similar case, the diffusivity coefficient calculation or determination of diffusivity coefficient accurately is very important. Because let's take, you have calculated one, you have designed one equipment, let's take 100 meter cube, and with diffusion coefficient equal to, let's take 1.5 into 10 to the power minus 6. But if the actual diffusivity coefficient is 155 into 10 to the power minus 5 instead of 1.5 into 10 to the power, then the volume of this your separator may reduce to 100 meter cube to 10 meter cube. So 10-fold decrease, you can understand that 100 meter cube equipment and 110 meter cube, how much cost difference that you are wasting. Or it may be you have been more estimative, you have calculated one separator 10 meter cube keeping the diffusivity coefficient is 1.5 into 10 to the power minus 5. But if it is actually 1.5 into 10 to the power 6, then with this separator, the separation won't take place. That is the waste. So, calculation of accurate diffusivity coefficient is very important, and that can be done in two ways. You can calculate this diffusivity coefficient through empirical equation. I am using this that word empirical. You have a already understanding in fluid dynamics. You use the friction factor for a turbulent flow. That was the empirical correlation. When people use the empirical correlation, when we cannot predict that phenomena with our knowledge, whatever theory we develop, if we cannot predict this one, okay, then people do some experiment, and they from this experimental finding they fit some experimental equation, and that is called empirical correlation. In empirical correlation, keep it in mind, there is no theoretical background. So this is based on the experimental. And second, you can determine the diffusivity coefficient from the experimental measurement. So that's why because accurate calculation of diffusivity is very important in separation process, that's why people use both. They calculate this diffusivity from empirical curriculum as well as they do some experiment. Then they make this, if they see, okay, whatever it is, let's take it is coming 1.5 into 10 to the power minus 5, here it is coming 1.4 into 10 to the power minus 5, that's mean it is accurate. Let's check, it is coming 1.5 into 10 to the power minus 6, and here it is coming 1.2 into 10 to the power minus 8, that's mean there is some problem. We should group the problem. That's why one is for calculation and another process we adopt to check whether it is correct or not. When both will be very marginal less, then we can confirm, okay, this calculation of diffusivity is correct. That's why people use both empirical correlation as well as experiments. Now I told that the gas phase diffusivity, first I will go the gas phase diffusivity DAB. The empirical correlation is one which is given by Chapman and Hengskog equation. These two scientists developed this empirical correlation, and that's why it is there. And what is the DAB? DAB equal to 1.858 into 10 to the power minus 7 t to the power 3 by 2 t to the power 1.5 into 1 by MA, capital MA plus 1 by capital MB whole to the power half, okay, by P sigma square, and this is D, and that unit is meter square per second. See, in empirical correlation, always they will tell what will be its unit, and it may not be unit consistent. Okay. But whatever is in there, where every parameter has to specify T absolute temperature, Ma, Mb the molecular weight of the components A, B. So you can understand with increasing molecular weight diffusivity will decrease. It is common factor. If you increase the amount, it cannot diffuse more. Bulky molecule cannot move fast, so diffusivity will decrease. If you increase the temperature, if you increase the pressure, it will decrease. So this thing, some quantitative thing, but what is this thing 1.858? So this thing is totally based on the experimental measurement. Now what is this? So sigma square AB and xi t. Sigma AB is the characteristic length parameter of the binary. It is in Armstrong. Okay, although this is meters per second, but this sigma AB, that will be this. Now what will be sigma AB? Sigma AB equal to sigma A plus sigma B divided by 2. Okay. Now what is sigma A? Sigma A is the characteristic length that depends on the 5 by 6 into Vc equal to the power 1/3. Vc is the critical volume of this component. For a particular component, critical state is defined, critical temperature, critical pressure and critical volume, it is well established. So I will show something, but there are, if you go in Paris, so if you, for a particular component A, so I can calculate sigma A equal to that corresponding Vc, for B corresponding, then I will take this, so I will get this, I will put it in the class. Now what is this? The collision integral, which is a function of Kt by EAB. Now what is EAB? K is the Boltzmann constant, T is absolute term, EAB, epsilon A into epsilon B whole to the power half. So this is the EAB. Okay, this is current. Now EAB equal to what? Again EAB E by K, this is equal to 0.75 into TC. So if you know for a particular component, critical point is required. When critical point is known, that means what is TC, Vc and Pc will be known. So from Vc you can calculate sigma, and from TC you can calculate the zeta, okay, epsilon. So one you will get the epsilon, this you will get. Okay. Now once you get this one epsilon, then from there how will you get the collision integral? Okay. So this is the thing what I am telling. So either epsilon you can calculate from this equation, and sigma from this equation in Armstrong and Kelvin, or this in tabulation form you will get this thing. In some books it will give you this thing. Okay, no problem. But Tc is the critical temperature, Vc is the critical volume. Okay, Vc is the critical, but unit is centimeter cube per gram mole. You have to use this one. Okay. Now that collision integral, this is equal to, if K by T by EAB, if this parameter is this, then it will be this. So accordingly, what will be this value? Accordingly, this will be your numerical value. See, all these are the parts of the statistical thermodynamics. Sigma is that xi. These are the part of the statistical. But you need not to know much, but you should know how to calculate this. So calculate is this thing is sigma, either sigma A calculate from this. If you know the Vc semi-gram, then calculate, or from that type of table. Okay, from that type of table you can calculate this one. Okay, then you calculate this, and this thing, to calculate this thing, first you calculate this, then this one, then you take this table, whatever the value of this, then you get this. This is very easy, isn't it? So from there you can calculate the diffusivity coefficient, and that is in meter square per second. Thereafter another equation, that is Fuller, Settler and Green. The three scientists, they develop another DAB. The constant is little bit different. Here if you see, it is T to the power 1.75. In that case it was 1.5, 3 by 2, but here something different. T and P is that, and 1 by ma plus 1 by mb whole to, it is similar, but they have instead of this they have used the other type of thermodynamic parameter, summation of Va whole to the power 3, summation of Va B whole to the power 1 by 3 square. Now T is temperature in Kelvin, mm molecular, P total pressure. Now I have to know how to calculate the V, summation of V. Okay, so V you can calculate. Let's take atomic and diffusion volumes. So for carbon, hydrogen, all these things are given. Okay, what will be the atomic? Now let's take, you want to calculate the summation of Va for cyclohexane. Cyclohexane means 6 carbon into carbon has a 16.5 plus 12 hydrogen, 12 into hydrogen 2.13, and cyclohexane means heterocyclic ring, so minus 2.1, so 106.5. so this will be your thing for cyclohexane. Okay, nitrogen, if you see the nitrogen, this is directly we will get the 17.9. so in this way, what is the system, you can calculate this one, you put this one and then you calculate, that will be in meter square per second. Okay, so there are two well-known empirical methods we presented here. From there you can calculate the diffusivity in meter square. Apart from this, some research also still going on. If you make the search, you will get number of equations. But which equation is applicable for your system, nobody knows. That's why whatever the possible empirical correlations are there, you calculate this thing from all this equation and see, compare these values. If you see that all are coming closer, that's mean all are applicable, it is very good. Then you do the experiment, and if you see whatever the diffusivity you have calculated from empirical, if it is matching, that's mean you can assure that your diffusivity coefficient is correct. Okay, now for liquid phase, okay, DAB 0 means DAB 0 is the diffusivity of solute in solvent mean in meter square per second. This is also meter square. The superscript 0 refers to an infinitely dilute solution, means solute A is very diluted. Okay, then 1.173 into 10 to the power into 16 and 5 B whole to the power half T. Here if you see, there is no temperature. In case of liquid, the diffusivity is proportional to T. In gas phase, it was 10 to the power T to the power 1.5 to 1.75. But in this case, this is T, and in gas phase, the diffusivity was inversely proportional to P. But in this case, there is no P. Instead of this, that is viscosity. Okay, so viscosity is there, and with this Va whole to the power 6. Okay, so different quantities involve a molecular weight of B. Okay, and this is the association factor for the different solvent. Okay, this is the association factor for the what are these, methanol this, ethanol this, non-acid solvent, that is will be 1. Temperature will be absolute temperature K, in my viscosity, solution viscosity in kg per meter square. So you have to that this thing the and SSI solute molar volume and normal boiling point in meter cube per Kelvin. Here that be a solute molar volume at the normal boiling point in meter cube per kilomole. So according to that unit, when you put this one, you can calculate the diffusivity coefficient for liquid Wilk-Jank equation, and that will be in meter square per second. Now we will calculate this diffusivity from the experiment. So experimental, here we will discuss one thing, the diffusivity experimental determination of gas phase diffusivity coefficient. There are two things, one is Stefan tube method and twin bulb method. So here we will discuss the Stefan tube method, okay, and in your mass transfer laboratory there this Stefan, you will do this experiment in your lab classes, mass transfer lab class, then you will use this one. So that how will you determine, now how will you determine this diffusivity coefficient in Stefan tube method? The arrangement is very simple. Let's take, I want to get diffusivity of acetone in air. Okay, now this is one T-shape arrangement, that is glass, made of glass. So this is hollow tube and this is one tube. Now what I will keep, I will fill this tube, half of this fill with the acetone, and here in this way I will set one pump here, small pump, we will put the air here and it will go out. So this is the very simple arrangement. Then this bath I will keep in one particular temperature. Let's take 60 degree centigrade temperature or 40 degree centigrade. If you keep this one, then what will happen? Acetone will be vaporized. Okay, so what will be the pressure here? What will be the vapor pressure of acetone at that temperature? That will be its pressure, because here only the vapor pressure of acetone is there, liquid. Then it will diffuse here, and then at this point when it will come here, then it will carry by the air. But keep it in mind, always whatever the pressure here will be the upstage pressure will be high, because always there is a evaporation, and because there is a concentration difference there in this point, the vapor pressure of liquid will be almost zero. Whenever it is coming, it is taken out. So that's why Pa2 at this point, that is equal to 0. Okay, vapor pressure of A means this acetone liquid at this point is 0. So, but gas cannot come here because here pressure is higher than this. So this is the diffusion of A through non-diffusion. So diffusion of Na through non-diffusion B, that's mean we will use this equation, Na equal to dAB P Pa1 means that is the here, from here that is the vapor pressure of this solute A, and Pa2 that will be 0. Okay, this. So this is the very simple arrangement. Now let's take at time 0 we have a liquid this, and after time dt, let's say there is a fall of this liquid dz. Okay, so dt will, let's take after 1 minute. Okay, some liquid will fall, and that is time I am telling dt time. For dt time, the liquid debit will drop because that this acetone or solute is diffusing from this tube to this there at steady state. So that's whatever is diffusing, because of that liquid, whatever the liquid sample is there, the level will form. But so this is the liquid acetone or liquid, and from it is gas, so that level will fall. Now how many moles in dt time, how many moles of solute diffuses, that what will happen? Let's say this is the cross section area A into dz, this is the volume. Okay, so A is the cross sectional area into dz, this is the volume. So this will be your volume into rho A, that much. Rho A means kg per volume, so that much rho A, if you take the kg by Ma, that is that kilomole. So in dt time, the dz is the liquid level low, and for that time how much moles of A diffuses? This much, because this is the volume. A is the cross section into dz volume into rho A, that is, this is volume meter cube, let's say kg per meter cube, then kg per molecular weight, that kilomole, that much kilomole is diffuses from here for dt time, and that will be equal to its diffusion rate. Now if you see, so A dz into rho A, this much of this thing, this much kilomole is diffused in dt time. Okay, so now what if this is the Na is the your flux, so flux into A, that will be your kilomole per second. Okay, this is kilomole per meter square second into, this is the meter square, so kilomole per second into time, that is kilomole. So this is kilomole, this is kilomole, that is the diffusion going on in dt time. Okay, so now if you put this Na, that A into dAb P, that is Pa1 minus Pa2 RT PBM Z dt, or Z distance. Okay, so now if you time t equal to 0 to time t dash, where the liquid level was here, let's take a time that was t0, that was z0, then at time t equal to 0, that is z0, and at time t dash, that is z dash, then it will be, if you integrate this thing at time t equal to 0 to t and corresponding dz, okay, that means z will be your that one. Okay, z dz. So then dAb will be RT PBM rho A z square z0 square by 2 PMA into Pa1 minus Pa2 into T dash. So if you for a particular, let's say you watch for time start, and after 5 minutes, that was a z0, and after 5 minutes t dash equal to 5 minutes, that is z0, this is the thing you are getting, right? So then from this, and this is the, this will be your the vapor pressure of solute. In this case, if you take the acetone, and this will be 0, we signal, so that's why we will calculate the diffusivity of A through B at that particular temperature this way. Okay, so this is very easy. So in this topic we talk about the diffusivity coefficients, because that is one important parameter in calculation of flux, and that will be used for designing the separation equipments. So accurate determination of diffusivity coefficient is very important, and we have seen for gas that diffusivity coefficient is 10 to the power minus 5 meter square per second, liquid it is 10 to the power minus 9 meter square per second, and for gas liquid it is around 10 to the power minus 12 meter square per second, in that range, and for gas it is 10 to the power minus 19 to minus 34 meter square per second. And we have shown number of examples on that. Then we want to calculate this diffusivity. There are two procedures. One is empirical procedure, and empirical procedure for particular phases. For gas phase we have seen two empirical equation. For liquid phase we have seen one equation, but keep it in mind, when you use this equation you should be very careful in its unit, because unit will not be consistent. Whatever The authors will tell you use this unit in this for this one, that for that one. Accordingly, you have to do this. And for there, we have seen that we have to use some statistical parameter based on the critical parameters of statistical thermodynamics. Thereafter, we have discussed one experimental method, Stefan tube method, to determine experimentally the diffusivity coefficient. So this is all about your molecular diffusion. Very simple chapter. You read it quite carefully, make notes on your notebook, that is very important. And in assignment also I'll give one question. You have to you make the notes on regular basis, so that, because at the end of the chapter I will ask you that please send me the notes, so then you have to just scan it. If you send it through PDF format. It is for every chapter. I will ask first question of assignment with that, and that is mandatory. If you don't do this, that's, I will assume that you are not following the lectures. Okay, so now we'll go for one interaction session, and whatever your doubts we will try to clear. Okay, thank you for your attention. Bye.